So we're talking in this lesson about the intermediate value theorem, and we don't spend a lot of time talking about theorems in our regular calculus course. But for the AP course, there are a certain number of theorems that they like you to be aware of. They want you to know kind of what those theorems are, and sometimes applying these theorems gives you a very quick way to show that something is true or give an answer to a question. So the intermediate value theorem is the first one we're going to encounter. So we're going to take a look at sort of an explanation of what the intermediate value theorem implies and how you can use it to solve a particular kind of question. So what I've got written up here is the text of the intermediate value theorem. If a function f is continuous on a closed interval from a to b, and there's a y value called k between f at a and f at b, then there's at least one x value called c, such that f at c is equal to k. Now, when I read something like that, I'm not entirely sure what it means. So it's helpful in a lot of cases to kind of draw a graph that represents what is just sort of being said there in words. So let's sketch out a little graph here. We're going to have an interval from A to B. Okay, and for each of those, for each of A and B, we are going to have a point. I don't know, we'll put a point here, and the y values of those points are going to be f at A and f at B. Okay, and we've got a function f that is continuous on the closed interval between those two functions. So let's just draw a continuous function that does something like this. Okay, continuous just means I can draw it without lifting my, my pen off of the screen here. So we've got a function continuous on the closed interval a and b. There's a y value called k, which is in between f at a and f at b. So we pick a y value, I don't know, right here. We're going to call this y value k. The theorem says that there is at least one x value called c, such that f at c is equal to k. So a y value that's equal to k would be somewhere along this line. And what we can see is that there are three possible values for c. There is this point right here, where f at c is equal to k. Or this point right here, where f at c is equal to k. And this point right here, where f at c is equal to k. So basically, what the intermediate value theorem is saying is that if you've got a y value, k, that is between two other y values, you're also going to have an x value that is between the two x values that correspond to your two y values. And this only works if your function is continuous, okay? And that's the big thing here, okay? The reason that there has to be that x value in between those two x values of a and b is because the function is continuous. The fact that the function is continuous basically means that you can't, as you're moving, let's say, from a to b, you can't just jump over any values in the middle. You have to hit all of the x values and all of the y values in between. So if there's a y value between our two y values, we have to hit a corresponding x value that is between our two x values, okay? Now, another way to think about a theorem is what would it look like when the conditions are not satisfied? So let's say we had a function. Well, let's start with our a and our b again. Okay, and then we'll give our 2 points here. So this is going to be f at a, sorry, f at b and f at a. Okay, f at a, f at b. Um, let's choose a k value in between. But let's say our function is not continuous as we go from a to b. So we could throw in something like a vertical asymptote in between. So if our function looked like this, approaching our vertical asymptote, you can see that because our function is not continuous, I'm not necessarily going to have that x value that corresponds to the y value of k in between a and b. Our function doesn't actually reach that value of k in between. Or I could have set up the function in such a way that, let's do this in blue here, let's say, that there was a hole in the graph right here. Okay, again, my function is not continuous. So it could be that at that exact value of k, there's a hole in the graph, so there is no x value corresponding to that y value of k. But again, in both of these cases, our function is discontinuous, so the intermediate value theorem doesn't hold. Now, the one application that I think we see most often in terms of this is using the intermediate value theorem to show that a function has a solution or a root on a given interval. Because if we have our function f on our closed interval, again, we'll do b and we'll do a, okay? If our function is such that, let's say, f at b is greater than 0, and f at a is less than 0, so let's put this down here like this. Let's be f at a way down here. And our function is continuous, then we can choose our k value to be 0. Then the intermediate value theorem that there tells us that there has to be some value of c in between a and b such that f at x is equal to 0, or sorry, at x equals c. So kind of showing that the function has a root at that point. So show f at x has a root on this interval from a to b. So let's look at this in terms of a specific function. Show that the function f at x equals cos x squared plus, cos squared x minus 2 sine x over 4 has a 0 on the interval from 0 to 2. First off, we have to notice that our function here is continuous. Okay. Why is it continuous? Well, the cosine function is a continuous function. Our sine function is also a continuous function. So combining two continuous functions together gives us another continuous function. So f at x is continuous for all real numbers. So it's certainly continuous on the interval from 0 to 2. So also on 0 to 2. Okay. Now, so in this example here, our a value is 0 and our b value is 2. Let's evaluate f at a and f at b. Now this would just be some calculator work here. We would sub 0 in to the function f at x, and we would get that f at 0 is 1. And then we would sub in 2 and get that f at 2 is equal to negative 0.786. So notice that this is greater than 0, this is less than 0, so we can say something like, therefore, by the intermediate value theorem, there is a value c on the interval from 0 to 2, where f at x equals 0. So it has a 0 on that interval from 0 to 2. Now, let's look at the same question for a different function. Show that the function y equals 1 over x minus 1 has a 0 on the interval from 0 to 2. We could start the same way. We could figure out, well, what is y at 0? That's going to be 1 over 0 minus 1. That's going to be negative 1. That's less than 0. We can evaluate y at 2. We get 1 over 2 minus 1, which is 1 over 1, which is 1, which is greater than 0. So in going from x equals 0 to x equals 2, our function goes from negative 1 to 1. This looks a lot like there should be a 0 in that interval from 0 to 2. What's the problem? The problem is that our function is not continuous on this interval. Because we know that at x equals 1, there's a vertical asymptote. So because the function is not continuous, the intermediate value theorem does not apply. So you could not use the intermediate value theorem to show that this function has a 0 on this given interval. So the question might be phrased something like, can you use the intermediate value theorem to show that the function y equals 1 over x minus 1 has a 0 on the interval 0 to 2, why or why not? And then you have to give like this little explanation. We can kind of confirm this with the graph of the function. We can see our vertical asymptote there at x equals 0, and you can see that on this interval from 0 to 2, there is in fact no 0 on this interval. Even though our a value and our b value, one is above 0, one is below 0, because the function is not continuous, it doesn't have to cross through 0 as we go from one to the other.